with the Academy of Science and Technology. What's a complex number? Numbers which can be expressed in the form x plus iy are called complex numbers. Here, x and y are real numbers and I is square root of minus 1 and it is imaginary. Is it imaginary? Yes, it is imaginary because we have the number systems, natural numbers, whole numbers, integers, rationals and irrationals. Next you consider the union of all these numbers and that's our real numbers. So now we have the real number system. See, in this number system, you consider a simple equation x squared plus 1 equal to 0. Next, you try to find solution of this equation. See, it's a second degree equation, so it has two solutions. See, we have to solve this equation. That is, we have to find the values of x which satisfies this equation. X square plus 1 equal to 0. That is, x square equal to minus 1. That is, we have to find numbers whose square is negative. Is it possible? No, it's not possible because square of any real number is positive. But here we have to find real numbers whose square is negative, which is not possible. So its solutions are imaginary. Algebraically, x square equal to minus 1 implies x equal to plus or minus root to minus 1. And we consider root to minus 1 as, see, it is imaginary and we denote it by I. So I is root to minus 1 and it is imaginary. So in addition to the real numbers, we have a new number I. Next, consider a new number system which consists of those numbers which can be expressed in the form x plus iy, where x and y are real numbers and this new number system is our complex numbers. And also notice that any complex number can be expressed in the form z equal to x plus iy. Next is representation of complex numbers in a plane. The set of complex numbers is two-dimensional and a coordinate plane is required to illustrate them graphically. This is in contrast to the real numbers which are one-dimensional and can be illustrated by a simple number line. The complex number plane is constructed by arranging the real part along the horizontal axis and the imaginary part along the vertical axis. Each point in this plane can be assigned to a unique complex number and each complex number can be assigned to a unique point in the plane. Really, there are two types of representation: Cartesian representation and polar representation. Let me illustrate Cartesian representation of a complex number. This x-axis has real part of z and y as imaginary part of z. See, our complex number z equal to x plus iy is the ordered pair xy. You mark the ordered pair xy. Let it be here. So this is our z. And this ordered pair xy is our complex number x plus iy. Suppose you wish to mark the complex number 2 plus i3. Then 2 plus i3 is the number. You take 2 units in the real axis and 3 units in the imaginary axis. Then plot the ordered pair 2, 3 and that is our 2 plus i3. Complex number 1 minus 2i. 1 minus 2i is the ordered pair 1 minus 2. 1 minus 2 is 1 minus 2. See, this is the ordered pair 1 minus 2 and the corresponding complex number is 1 minus 2i. Next, can you mark the complex number I? First you express in the form of an ordered pair. I is, its real part is 0 and imaginary part is 1. I is 0 plus 1 into I. So it is the ordered pair 0, 1. And 0, 1 is, and this point is I. And this point is minus I. Similarly, you can mark any complex number in this plane. See, our complex number Z is the ordered pair xy. Next, you consider a reflection of this point along the x-axis. And it is here with the x minus y. See, this is the reflection of the point ordered pair xy along the x-axis. And the corresponding complex number is x minus iy. It is known as the conjugate of x plus iy, and it is denoted by z conjugate. So, if z equal to x plus iy, its conjugate is denoted by z conjugate and it is x minus iy. And conjugate of this number is a reflection of this number along the x-axis, and it is xy. So, conjugate of this number, conjugate of z conjugate is x plus iy. It is z. So, we can obtain conjugate of any complex number by replacing I by minus I. See, we have z equal to x plus iy, z conjugate equal to x minus iy. So, what is x? X equal to z plus z conjugate by 2. That is, our x is a real part of z. Similarly, what is y? Z minus z conjugate by 2y. That is imaginary part of z. Next, see, this is our z and this distance is mod z. Mod z. Next, you consider the right angle triangle and this is y and it is x. So what is mod z square by Pythagoras theorem? It is x square plus y square. Mod z square is x square plus y square. From here, what is z conjugate? Z conjugate is x square plus y square. But x square plus y square is nothing but our mod z square. So we have mod z square is z conjugate. These are some basic properties of z and z conjugate. Next, polar representation of a complex number. Consider a complex number z equal to x plus iy. Assume z be this point. You consider mod z. See, this is our modulus z. Let it be r. You consider the right angle triangle. Clearly, it is y and it is x. You measure this angle. Let it be theta. Then, what is sin theta? Sin theta is y by r. Cos theta is x by r. See, our complex number is z equal to x plus iy. From this, x equal to r cos theta. From here, y is equal to r sin theta. So, r cos theta plus I r sin theta. R is a common factor. Cos theta plus I sin theta. We know e raised to I theta is cos theta plus I sin theta. Now we have z equal to r e raised to I theta. Here theta varies from 0 to 2 pi. And r is mod z. See, mod z is root x square plus y square. So we have another representation of z like this. Z equal to r e raised to I theta. And this representation is known as the polar representation of the complex number, or the modulus and argument form. Here r is called the modulus or absolute value of the complex number. The angle theta is called the argument or amplitude of the complex number.